question is, how do we test this PSRAM? Well, this is a neat little routine, and I'll tell you where I got it from in a while. But it involves an octopus, let's put it that way. But what this is doing is saving an address in each 32-bit address. So it's noting the time and then going all the way through the memory, all 64 megabits of it, and saving an address in each 32-bit address. And then it goes back and reads the same data back and compares it. So if it doesn't get the address of its address back, then it would print a PSRAM failure. Otherwise, it completes and it will give us some stats as to how fast the memory was written to and read from. Hope that makes sense. What that looks like is it's writing to the memory. There we go. And then reading back 8 megabits of 32-bit data. Okay, there we are. What does writing 8 megabits in 9.8 million microseconds actually mean in terms of sample rate that we can stream to RAM? So that will be 9.882077 seconds divided by, we already know that we can fit 2,097,151 samples into memory, and reciprocal of that, so that's 212 kilohertz on the right, and so for the read that is 10.835538 seconds divided by 2,097,151 is that reciprocal 193. So we can write at 217 kilohertz and we can read at 193 kilohertz. Remains to be seen whether that gives us enough time to actually process the data in between reading and writing. So we'll see. So I'm frankly concerned about the speed of the SPI bus, and I don't like the idea of functions that are called read blocking and write blocking. It sounds like they're going to get in the way of some of the processing we need to do. So I've been Googling around looking for other implementations of SPI PSRAM on the RP2040 and came across this project, the Pico, and it's the brainchild of somebody called Ian Scott, who goes on GitHub by the name of Polpo, Italian for octopus. See where I came from there? And this is using the RP2040 microcontroller to emulate the Gravis ultrasound card, and in fact several others, the Sound Blaster, Game Blaster, etc. And yeah, I had a Gravis ultrasound back in the day. I used to write audio editing software, and my distributor gave me one when they first came out. I wish I'd kept it because it seems they're worth money nowadays. But anyway, Ian Scott, as part of this project, has written a SPI PSRAM interface, and I'll show you that now. And here it is. He calls it a header-only C library to allow access to SPI PSRAM via PIO. These are the little state machines that I've talked about before on the RP2040 microcontroller. And he said he was having trouble getting PSRAM working at speeds greater than 84 megahertz. Now, I was only running it at 33 megahertz, and I was worried about the speed. And he said so he's written this header-only library, and he says he's tested it on, and look at this. This is the AP6404, which is the memory chip that I've been using. These chips have been tested as stable up to a clock speed of 280 megahertz, creating a SPI clock speed of 140 megahertz. So that's, you know, a good 3 times, maybe 4 times the SPI bus speed that I've been testing at. So I'm going to give this a look. This is Polpo's RP2040 PSRAM repository, and we can clone it with this git command. But he also includes a test program here. So he's got quite detailed instructions on how to use the library, what restrictions there are on pins. The CS and SCK must be on consecutive GPIO pins, for example. How to build it, how to configure those pins. So yeah, it looks very straightforward. Following Ian's instructions, I've had to jiggle the pins around. Chip select needs to be adjacent to serial clock, with the chip select on the lower of the GPIO pins. So I've kept the same pins, but I've had to change them. So this is master out, and this is master in. This is Ian's RP2040 PSRAM SPI.h file, and this is the copyright notice. So I understand it, this is an MIT license, which is really very permissive, so I can use this, and provided I include the copyright notice. So thank you, Ian. I think I understand a lot of what he's doing in this code, but it's quite complex. But I just want to highlight his comments, which are all written with a view to them being digested by something like Doxygen to generate documentation and to document the source code. And this is lovely. It's really professionally written, very neat, tidy, well documented code explaining what all the parameters do. So yeah, hats off to Polpo. The definitions of which pins, GPIO pins that is, are used for chip select, serial clock, master out and master in, are in the makelists.txt file that's included with the PSRAM test program. And so I'm just going to build this. Yeah, I mean it compiles straight away, and we'll test it, see what sort of performance we get. So this is running Ian's test program, writing and reading 32-bit bytes, and there we are. Let's compare the results. So I've just popped the results into a spreadsheet, and these were the results I got from my SPI program at 33 megahertz. It took 9.8 seconds to do the 32-bit write and 10.8 seconds to do the read. And these are Ian Scott's results. So 9.8 seconds plays 2.1 seconds. So that's a 4.5 times improvement in write speed. Read speed, not quite such an improvement, 2 3/4 times an improvement, but 10.8 seconds plays 3.9 seconds. So yeah, pretty impressed with that. I have a pretty good feeling about that SPI memory chip, the 6404. So I've put it back into this circuit on this breadboard and wired it back in exactly the same as when I was just testing it. So I've now got decent quality input here, stereo analog to digital converter, decent quality output, stereo digital to analog converter, and I've got enough memory for about 20 seconds of stereo buffer. So, time to have a play.